Hello everyone, this is Abhishek and my teammates Litish and Saicharan. Today we are going to present our final project design studio. So our project is titled as Root Cause Suggestion for Outages using Log Embeddings and Similarity Search. So over the 10 minutes, we will walk through the problem we identified, the solution we designed, the results we achieved, and the lessons we took away from this experience. So I'll start by covering the problem background and the research aim. Litish will then take us through the literature and our implementation, and then Saicharan will close with our results and conclusion. So here's a quick overview of what we have covered today. Coming to the outline, we will walk through 7 areas: the problem background, our research, question and aim, a review of relevant literature, how we build the system, the results we got, and the conclusions and recommendations, and finally a brief reflection on what we learned as a team. Let me jump through the straight into the problem. Coming to the problem background, the problem we are addressing is one of that affects every organization running distributed IT systems today. So, coming to the problem that affects every organization running is the modern systems, the cloud platforms, the banking application, e-commerce generate millions of log lines every single hour. So when something goes wrong and an outage happens, engineers need to find the root cause fast, but the traditional approach of manually searching through logs using keyword is slow and inconsistent and unreliable. There are three core reasons why this way fail. First one is the volume is simply too large for manual review. Second, keyword search breaks down under pressure and it is error prone and time consuming. And third, the same underlying issue can appear with completely different wording across different services. So a keyword match will miss entirely. This is the gap we set out to close. Coming to the research problem and aim, our central research question is how can we build a scalable system that semantically understands log data and uses historical incident knowledge to recommend root causes quickly and accurately during an outage. The aim is to design a design support system that converts raw logs into semantic vectors and uses those to find historically similar incidents and suggest ranked root causes. We have structured this around three core objectives: building a labeled incident dataset, developing an embedded based similarity search engine, and demonstrating that our approach outperforms the traditional BM25 keyword baseline. I will now hand over to Litish, who will be continuing with the remaining slides.
Thank you, Abhishek. Thank you for your wonderful presentation. Now I am presenting the literature review slide. When we reviewed the existing approaches to log-based root cause analysis, we found three broad categories. First, traditional routes like Elasticsearch and Splunk use keyword search, and it is very easy to deploy, but they completely fail when the same problem is described with a different terminology. For example, Johnson ETL and 2017 documented these limitations clearly. Second, ML models like Deeplog and Lobert detect anomalies automatically. Different terminology, but they flag that something is very wrong without explanation. Why engineers still investigating manually? Uptime Institute of 2024 outage report shared that showing this gap continuously to cost organizations significant downtime. And third one is where our project sits, embedding based similarity search, better based transformers, encode logs as semantic vectors, and fastest vectors. Similar historical incidents, even when the word is completely different, and Delvin, etc., 2019 established this foundation. This research gap is clear, and no existing system combines this embedding with a structured root cause suggestion mechanism. Our project fills with exactly the gap. And now coming to implementation slide. Now let me walk you through how we build the system, the five-stage pipeline on this slide. In the first stage one, it's a log ingestion. In the first slide, we will collect system data and application logs from the distributed service environments. In the stage two is pre-processing. Using Python and Pandas, we clean it the logs, removing noise like timestamps and IDs, and normalize the data. In the stage three is embedding generation. We use it based NLP models to convert each log entry into semantic vectors. This is the key step. Instead of matching all the exact words, the system understands the meaning of the log. And coming to stage four is vector indexing. We use FASIS and Elasticsearch KNN to index all embeddings for fast similarity searches. And now coming to stage five, it is the RCA suggestion. When a new outage log comes in the system, we use the top key most similar historical incidents and generates a ranked list of likely root cause. This full stack includes Python, NumPy, Pandas, and but embedding FASIS and OpenSearch. Yeah, now I will hand over to Sai Chavan from my friend for our results.
Thank you, Litish. Thank you for your presentation. Now I'll be continuing with the presentation. I'll explain the slides 11, slide 7. Uh, I'm Sai Charan. Our evaluation measured 4 key metrics. We achieved over 70% top 5 retrieval accuracy in more than 7 out of 10 cases. The correct root cause appeared in the top 5 results. Root cause assertion accuracy at top 3 came in above 60%, meeting our predefined target. Query latency was under 2 seconds, making the system viable for real-time use during live outages. And critically, our embeddings approach outperformed the BM25 keyword baseline by approximately 22% in retrieval accuracy, directly validating the core hypothesis of our project. At the module level, every component performed as designed with no data loss. Coming to the next slide, to summarize, embeddings-based similarity search is significantly more effective than conventional keyword methods. Our prototype met every performance target we set. For organizations looking to implement this, we have 4 recommendations. Expand the incident data sets to 100 plus labeled incidents, integrate with ITSM platforms like PagerDuty or ServiceNow, pilot in staging environment first, and build an engineer feedback loop to continuously fine-tune the model over time. The last slide that this brings us to the end of our presentation. This project taught us good system design starts with a well-framed problem. The technical work only holds together when the research questions and objectives are precise and measurable. Thank you so much for giving us this opportunity.